Now, last time in your AS physics, you would have learned something called unified atomic mass, where the main thing that was mentioned to you that time was that we mentioned that U is 1.66 times 10 power minus 27 kg. It was actually the approximate mass of one nucleon. Okay, so this was what we mentioned to you last time in AS nuclear physics. Now, specifically when you're thinking about U, masses, you can think of U as just another unit of mass. When you're dealing with the chapter on nuclear physics, you'll be doing a lot with the masses of nuclei. And usually when you're talking about the masses of nuclei, they're usually expressed in terms of U. Okay, you see in the tables here, we give you a number of nuclei, electron, neutron, proton, hydrogen atom, helium atom, alpha particle, and so on and so forth, right? So note that all these masses can be expressed in kg, but usually the standard is that rather than expressing them in kg, we tend to express them in terms of U. Okay, you can just think of U as just another different unit of mass. All right, so all the masses that you see here are actually in terms of U. All right, and when you do your calculations in this chapter, in the chapter of nuclear physics, a lot of times your workings will involve up to 6 or 7 SF. You can see here, all these masses that are listed here are all the way up to 7 SF. All right, the usual standard last time was that you were only working up to 2 or 3 SF. All right, but in your current case, when you're dealing with this specific chapter, questions from this chapter, usually if they give you the masses that are up to this number of SF, you need to maintain this number of SF in your working. All right, because the thing here is that when you're dealing with subatomic particles, the difference in mass is really small. So when the difference in mass is really small, you need to work to a larger number of SF. For example, if I tell you the mass of a neutron versus the mass of a proton, these are the exact values in terms of U. Okay, you notice that up to 7 SF, you can actually see a difference in their value. But if I were to tell you to work up to 2 or 3 SF, say for example, this one I ask you to work up to 3 SF, this one will become 1.01 U. This one will also become 1.01 U. So when you look at it this way, if I look at it in a small number of SF, there's virtually no difference between the mass of a neutron and the mass of a proton. But if you were to work up to a larger number of SF, you can actually see the difference there. That's the reason why here in this chapter, when you're working with their masses, you have to work up to a large number of SF. Okay. In your AS last time, you remember in AS physics, a lot of your workings were up to 2 or 3 SF only. Okay. So that time I told you that the U is actually the approximate mass of one nucleon, where a nucleon is actually your proton or neutron. Okay, so the reason why I said that was because since you're only working up to 2 or 3 SF, you notice that there's no difference between their masses. Okay, that was what we told you last time in AS physics. If you're trying to find out, say, the mass of a nucleus, what you did was that you take the nucleon number, multiply with U. You take the total number of protons and neutrons, multiply with U to get the mass of the nucleus itself. Because that time we assume that 1 U is actually the mass of one nucleon. Okay, that was the idea there. But now you need to be careful. Mass of neutrons and protons are not 1 U. They are actually up to a larger value. Okay. Now, the values that are listed here, you don't really need to memorize them. If you are required to use them, your question will tell you. Okay, that's just what I want to mention to you when you're dealing with masses of subatomic particles here. Now, also another thing that you should know now from here is this. There's this concept of missing mass and binding energy that you need to know. In your AS physics last time, in AS physics last time, it was mentioned to you that when it came to the quantities that are conserved, it was mentioned that if you say that mass is conserved, it is wrong. If you say that it is energy that is conserved, it is wrong, right? What is actually correct is to say mass energy is conserved. Okay, remember this from your AS physics. When they ask you what are the quantities conserved, you will say proton number conserved, nucleon number conserved, momentum is conserved. But then when it came to mass and energy, you cannot say mass is conserved or energy is conserved. Instead, you need to say is mass energy conserved. All right. There's a reason why we say that mass energy is conserved here. Now, an example of that is this. If I tell you to look at the mass of if I tell you to look at the composition of an alpha particle is alpha 42, you have 2 protons as well as 2 neutrons. So if you try to draw out their nucleus, you will see that there's actually 2 neutrons and 2 protons. Okay, this is if I'm talking about the nucleus itself for an alpha particle. But I know that they are actually made out of 2 individual protons, 2 individual neutrons. Okay, so I have 2 individual protons as well as 2 individual neutrons. This one here would be my neutrons. Okay, so the thing here is this. When you want to get a alpha particle nucleus, you need to combine the protons and neutrons together inside the nucleus. Okay, they need to be combined together or squashed together to form a nucleus. But the thing here is this: when they actually try to sum out the masses of your nucleons, if they try to sum out the mass of your nucleons and they measure the mass of the nucleus itself, you would have expected that the masses are the same because the nucleus is actually made of the neutrons in the first place, right? But the curious thing is that when they actually try to verify this, where they add up the individual masses of the neutrons and then trying to compare with the actual mass of a nucleus, what they found out was that the mass of the nucleus is actually not the same as the mass of the neutrons. What they actually found out was that the mass of the nucleus is actually less than the sum of the mass of the neutrons itself. There is actually missing mass. And there is actually missing mass. When you take these these 2 protons and these 2 neutrons and then you combine them together inside the nucleus, somehow or another the nucleus is actually lighter. There's actually missing mass here. So where did the mass actually go to in the first place? How come the mass suddenly disappeared? The idea here is this: if you remember that proton is actually positively charged, when you try to put the protons together close to each other, the protons generally tend to repel each other off because they're both positively charged. So the thing is that the neutrons were able to fit together closely inside the nucleus despite the repulsion of the protons. So this one actually tells you that some energy or some sort of force must be holding the protons together. In other words, some sort of work must have been done to hold the protons together. So the thing here is this: that energy to hold the protons together, the work that has been done to hold the protons together actually must come from somewhere. It actually came from your mass. Okay, so let me just draw the arrows here. If you went from here to here, okay, in order for you to have the protons close to each other inside your nucleus, some sort of work must have been done in order to hold them together. or rather you can think of some sort of energy must have been used to hold them together. The energy must come from something. According to conservation of energy, right? Energy cannot just come out of nowhere. So your energy must come from somewhere here. All right. So the energy here actually came from mass, from the missing mass. So here, if I wanted to combine these two protons and these two neutrons together inside a nucleus, what actually happened was that mass is converted to energy in order to hold the protons together. Right? So the idea is just that protons have repulsion. If you bring them close together inside the nucleus, they will repel each other off. So something must be holding them in place. Some sort of work must have been done. Some sort of energy must have been expended in order to hold them in place. So the energy must come from somewhere. So this energy came from your missing mass. Okay, that's why here when we say what quantities are conserved, we actually do not say mass is conserved, because when we compare the mass of the nucleons and nucleus, they're not the same. And then we also do not say that energy itself is conserved, because here the energy that was used to hold the protons together did not come from other forms of energy. Instead, it actually came from mass. So it's not correct to say energy is conserved. It would be more correct to say that mass energy is conserved. Mass is converted to energy. The converse, the reverse is also true. Energy can also be converted to mass. All right. So you see, if let's just say, for example, I want to break the nucleus into the individual nucleons, what would happen then is that energy is converted back to mass, no? All right. So it works both ways. If I take off some of the masses, it will be converted into energy to hold the nucleons together. But then when I go and break them apart, energy is released back and is converted back to mass. So when you break the nucleus apart, you're going to get back the mass of the individual nucleons. Okay, right? So that is the idea here. Okay, now mass defect, the difference in mass when you have the individual nucleons and the actual nucleus itself is actually what you know as mass defect. Okay, is the difference between the mass of your nucleus and total mass of your nucleons when the nucleons are separated to infinity. Okay, so this is what mass defect is. It is actually denoted by the symbol delta M. Okay, now for mass defect, you have something else called binding energy. All right, binding energy is a definition that you will need to learn, where did we tell you binding energy is equal to the energy needed to separate a nucleus into individual nucleons completely to infinity. Okay, so when you want to break apart the nucleus, you need to supply energy in order to break it apart. So to the energy that you supply to break it apart into the individual nucleons is what you know as binding energy. Okay, so if you go from nucleus to nucleons, this one is what you know as binding energy. Whatever energy that you supply in order to break it apart into the individual nucleons, that is what we know as binding energy. And to find out the binding energy, there is actually a calculation that you can use. That one is this equation here. E is equals to delta mc squared. You have seen this in SPM before. I think they call it Einstein equation, right? Or something like that. They say it's from Einstein. Yes, it is from Einstein. You specifically use this for nuclear reactions. All right. So here, when you want to find out binding energy, you use this equation. E is equals to delta mc squared, where delta m here is actually the difference in mass between your nucleus and nucleons. Okay, this one is already defined here. And then your c is your speed of light, which you have to square eventually. All right. Okay. So binding energy was defined as that. All right. The energy that is needed to separate a nucleus into individual nucleons completely to infinity. Now, what do we want to use binding energy for usually? Binding energy is actually related to stability of your nucleus. Okay. So in general, what we'll tell you is this. When we want to compare the stability of different nucleus or different nuclei, binding energy per nucleon is something that we would consider. In general, when binding energy per nucleon is higher, your nucleus is considered to be more stable. Okay. BE binding energy is a measure of stability, simply put. Okay. So the higher, if you see the binding energy per nucleon increase, stability generally increases. Okay. Now, when something is more stable, it means it's harder to pull it apart, right? Okay. When you're talking about a nucleus, let's just say a helium particle, sorry, a helium nucleus like this one. If you need more energy to pull the nucleus apart, that means it is stable. If you need less energy to pull it apart, that means it is less stable. Okay. All right. That's why here, when we tell you something has higher binding energy per nucleon, it tells you that for one nucleon, you actually need to put in more energy to separate it. So when you need to put in more energy to separate it, obviously this implies that the nucleus is actually more stable. If some nucleus is more stable than the other, you will actually need more energy to pull it apart. Okay, so binding energy per nucleon is a measure of stability here. And then from there, you will need to consider something. There's a particular graph that you would need to know. You need to memorize the general shape of that graph. Okay, so the graph that you need to memorize eventually is this thing called binding energy per nucleon versus nucleon number. Okay, binding energy per nucleon versus nucleon number has this general shape. Okay, wait, let me just draw it here. It could be something like this. Let me just try this first. This is BE per nucleon. This is nucleon number. Okay, so binding energy per nucleon versus nucleon number has this general graph shape. Again, you need to remember this graph and certain particular points related to this graph. Now you see, when you're looking at the graph for binding energy per nucleon versus nucleon number, you need to remember where the peak is. The peak is over here, and this one is 56. This point here is actually the most stable. Okay, remember just now I told you binding energy per nucleon is a measure of stability. The higher the value of binding energy per nucleon, the higher the stability, right? So you see this particular point here at the peak is where your binding energy per nucleon is the highest. It's actually the most stable. This one belongs to ferrum 56. Okay, so you just really need to remember this general shape of your graph and where the peak is at. Okay, it is always at 56. At ferrum 56 is the most stable element. So later on you'll see sometimes they may give you some question. If I tell you I have a element uranium 238, and then after that I have something lanthanum 128, and then maybe I have something like some other element, maybe X32, they'll ask you to indicate on your binding energy per nucleon graph where are the positions. So it could be that maybe for uranium, 238 is over here. For lanthanum is 128, right? So 128 would be probably over here. So this is lanthanum. and then this is uranium. And then for this element X with nucleon number 32, it will be somewhere here. Okay, this one is here. All right, it's all made with respect to where your 56 is at. If you see the nucleon number is above 56, it will be on the right hand side. If your nucleon number is below 56, it will be on the left hand side. Okay, that's the reason why you need to remember the general shape as well as the position where you have highest binding energy per nucleon. All right. Okay, now apart from this general shape, the actual binding energy per nucleon graph actually has 3 peaks. You will have one peak here, second peak here, and third peak here. That's what you're looking at over here. Okay. Now, those peaks belong to hydrogen. Sorry, those peaks belong to your helium nuclei, carbon nuclei, as well as your oxygen nuclei. Now, the reason why they seem to be giving you a peak is because what we'll tell you is that the okay, the reason why you suddenly have the peaks here is because these 3 elements, helium 4,2, carbon 12,6, and oxygen 16,8. This one we will say that they are more stable than usual. Okay, because if you follow the general trend line of the graphs, it's supposed to look like this. Okay, but then somehow or another, those 3 elements are giving you a peak like this, and like this. So it's giving you a higher binding energy per nucleon than usual, than what you expect. That's the reason for that is that they're actually more stable than usual. Okay, the configuration is more stable than expected. Okay, but in your exam, you actually do not need to know what are the 3 elements that are more stable than usual. Okay, you are not required to know what element would the peaks belong to. Okay, you're not required to explain why the peaks are there. Okay, so this one is just some extra knowledge. You don't need to bother about that. You really just need to bother about the general shape and where the most stable element is at. Don't bother about the peaks. All right. Okay, now this graph also will allow you to explain whether certain elements are going to undergo fusion or fission in the first place. All right, so this one we will revisit a little what you learn in SPM physics. In SPM physics, you learn nuclear fission and nuclear fusion, right? So nuclear fission is just defined as when an unstable heavy nucleus absorbs a neutron and then splits into 2 daughter nuclei of equal masses and more neutrons to become more stable. Okay, fusion is where a heavy nucleus breaks apart into a smaller nucleus, all right, of about equal masses. And then fusion is the direct opposite of that, where we tell you for nuclear fusion, you have 2 light unstable nuclei that join together to form a heavier, more stable nucleus. Okay, it's the direct opposite of fission. Fission is large, heavy nucleus break apart into 2 smaller nuclei. Fusion is when 2 light unstable nuclei join together to become a heavy, stable nucleus. Okay, so that's fission and fusion that you've learned before. So this graph actually would allow you to tell whether something is going to undergo fusion or fusion in the first place. Take for example, if I look back at the graph, I have this element, uranium-238. Now, if uranium-238 wants to become more stable, it could either go down or go up, okay? So you understand that for any nuclear reaction, the goal is always to become more stable, right? So if I have a element, if I start off with a particular element in my nuclear reaction, which is uranium-238, if I go down the graph, I'm actually becoming less stable. Because you see, if you follow the curve, if I go down, my binding energy per nucleon is actually dropping in value. So I'm actually becoming less stable. But if I go up the graph, my binding energy per nucleon is actually becoming higher. So I'm actually becoming more stable. So when anything undergoes some sort of nuclear reaction, the goal is always to become more stable. So if I have any reaction that will occur for uranium-238, since the goal is always to become more stable, it will actually tend to move up the graph. Okay, but again, you will notice one thing. If you try to move up the graph, what happens to your nuclear number? If you go towards the left, your nuclear number is actually decreasing. So if you're starting off with uranium-238, after your nuclear reaction, you're supposed to become more stable. So whatever you have after that, the nuclear number should be less than 238. It should be less than before because your nuclear number is decreasing. So the only way your nuclear number can decrease is if you're undergoing fission. Because fission just now in the first place is where your nucleus splits apart into two other nuclei, right? So when you split apart into two other nuclei, your nuclear number actually would drop. So here, we know that given any element on this graph, if it wants to become more stable, it has to go up the graph. So it's undergoing fission due to the fact that your nuclear number is decreasing. Okay, so the similar argument can also be thought of if you're starting with an element from the left side of the graph. Say for example, I tell you you have a lithium element, lithium-63. If you were to undergo some sort of nuclear reaction, it has two choices. Either it goes up or either it goes down. But here you see when you're going down, your nuclear number is your binding energy per nucleon is decreasing. You're actually becoming less stable. But if you were to go upwards, your binding energy per nucleon is actually increasing. So this one you're becoming more stable. So you know that whatever nuclear reaction that occurs, you would actually be going upwards. But in the process of you going upwards on the graph, you will notice that your nuclear number is actually increasing. So it means to say that your nucleus is actually getting larger because the nuclear number is increasing. So the only way your nuclear number can increase is if it fuses together or combines together with another nuclei. So we know that it will tend to undergo nuclear fusion. Okay, so that's what this graph is actually trying to tell you. For any elements on the right hand side, if it wants to become more stable, it will undergo fission. For any elements on the left hand side, if it wants to become more stable through a nuclear reaction, it will undergo fusion. Okay, so there's the idea here. Okay, so we stop here. Let's just do some questions. The rest of the other concepts and this one I think we can do after we've done the questions. Okay, right. So let me just open up the ask you a question. Okay, so nuclear physics. Let's have a look at those questions. Wait, now where's the nuclear physics? Nuclear physics, page 25 and 20. You know. Okay, just have a look at page 25. We start off with this one first. Okay, this is March 18 P4. Okay, so let's have a look at that. Let me just open it up.
Okay.
Okay.
Yeah.
All right. Right. So you have this one. Right. So this is the thing that I was talking to you about. All right. So one particular fission reaction may be represented by this equation, blah, blah, blah. The reaction with nucleon number A of the binding energy per nucleon Be is as shown here. On the same figure, mark on the line positions of uranium-235, barium-141, and krypton-92. Okay, so here, you see this is the graph that you're seeing in notes. Here, they're asking you to label the positions of these three elements, uranium, barium, and krypton. So I mentioned to you that for that graph, the peak always belongs to ferrum 56. So anything with a nucleon number more than 56 must be on the right side. Okay, you can just think of the 56 as being your reference point on this graph. Anything with nucleon number less than 56, it will be on the left hand side. But anything with a nucleon number more than 56, it will definitely be on the right hand side. Okay, so uranium-235 will probably be at this edge here. This one will be 235. Barium-141 is slightly less. It will be over here. And then after that, krypton-92 will be somewhere over here. Okay, so you're supposed to indicate the positions around here. Okay, and label them according to the elements, uranium, barium, and krypton. Okay, so this is the easiest one to see when it comes to binding energy per nucleon graph. Okay, so this is one. Okay, right. Then I move on to another one. This one, next one will be page 20. Yeah, I think it's page 20. Binding energy. Okay, yeah. Next one you go through is page 20. Right, so we go through page 20. Okay, it's 5 pages before. Right, this is June 17, P42. Is nuclear physics question is almost always the last question you will do in your paper 4. It's either question number 10, 11, or 12. Okay, all right, so look at the question. This one, they tell you that one nuclear reaction that can take place in a nuclear reactor can be represented by this equation. All right. Then they tell you data for nucleus and some of the particles are given here. All right. And they're all given in terms of U. And you notice they're all given in a large number of SF. They don't give you in just 2 or 3 SF. They give you all the way up to 6 SF. Okay. Now, they are asking you for part A, complete the nuclear reaction shown above, which is basically this particular reaction here. Okay. This one, this one, this one, and then there's a missing blank here, right? So you're supposed to find out what is the element here. What should be going to the missing blank there? All right. So this one is something that you will be very familiar with from your experience from AS physics. You need to balance the nucleon number and proton number. You need to balance both sides. Okay. So if you look at the proton number side, this one, if you look at the proton number, this one is 92. Okay. Before the reaction. After the reaction, the proton number should also be 92. But then when you count the proton number from here, this one 42 plus 57, 42 plus with 57 was supposed to be 99. So you need to add -7 in order to give 92 back. So the only element that has a negative, the only element with a negative for the proton number is only electron, right? Okay, because you see your proton number, you need to add with something that is negative in order to bring it back down to 92. The only element that you know that has a negative is electron. How many do you need to get negative 7? You need 7. So here, that's why you have 7 electrons. Okay, you can double check again with your nuclear number at the top just to be sure. Your nuclear number at the top is going to be 236. So after the reaction, your nuclear number must be 236 also. So let's try and add up all your nuclear numbers, see whether you're getting 236. You would have 95 plus with 139 plus with 2 plus with 70. You by right should get back 236. Okay, so you putting electron is the correct one. Okay, so that's how you complete this. You have to balance the proton number and the neutron number, see whether they tally. Okay, so this is from your AS physics. Okay, now the next part here, under part B, if you look at part B1, they ask you show the energy equivalent to 1U is 934 mega eV. So just now what I explained to you was that I mentioned something about mass energy conservation, where basically it says that mass can be converted to energy, and then likewise energy can also be converted to mass. This is what mass energy conservation actually means. So what they're asking you right now is this: if I have a mass of 1U, show that the amount of energy equivalent to 1U is actually 934 mega eV. And that's what they're asking you. Show that the amount of mass that 1U, show that the amount of energy that the mass of 1U contains is 934 mega eV. Okay. Now, EV, I think you learned already. You gone through electric field already, right? I think in A2, your teacher has gone through electric field, has he?
Yeah.
Okay. So, what do you remember about EV? Don't know.
The unit times something joule one.
Okay. EV is another unit of energy. Just like I mentioned to you just now earlier on in the lesson, 1U is actually another unit of mass, whose value is 1.66 times 10 power minus 27 kg, right? So EV is also somewhat similar, just that it's for energy. 1 EV is actually another unit of energy, where we tell you 1 EV is actually 1.6 times 10 power minus 19 joules. Okay, so if we ask you what is the value of 1 EV, is actually 1.6 times 10 power minus 19 joules. All right, it's just another unit of energy. That's all there is to it. So when we ask you what is 1 mega EV, you see that there's a big M then EV there, right? That big M is actually just your prefix. It's actually talking about mega EV. So 1 mega EV is actually 1 times 10 power 6 EV, which in turn is actually 10 power 6 times 1.6 times 10 power minus 19 joules. Okay, that's what 1 mega EV actually is. All right. So they want you to show that the energy equivalent to 1 EV, the energy equivalent to a mass of 1 U is 934 mega EV. So let me just mention this thing to you first. When you want to change from EV to joules, you multiply by 1.6 times 10 power minus. when you have EV, you want to change to joules, you multiply with 1.6 times 10 power minus 19 joules. When you want to change from joules to EV, you divide by 1.6 times 10 power minus 19 joules. Okay, this is the conversion that you are looking at. From EV to joules, you multiply. But from joules to EV, you need to divide. Okay, so let's just find out the energy associated with a mass of 1U in joules first before we convert to EV. Okay, so just now I told you that there's a particular equation that can be used to find binding energy, which is this one. Wait, let me just go back a little. Just now I told you that if you want to find the binding energy of a particular nucleus, you can use this one, right? E is equals to delta mc square, right? I forgot to mention this to you. It can be used to find binding energy, that's correct. Specifically, E equals to mc square is used to find energy caused by mass changes. Energy associated with mass change. Okay, wait, let me just rewrite this. E equals to delta mc square in general can be used as, is in general used to find energy associated with any mass change. Okay, with any mass change. Wait, let me just write properly here. Energy associated with any mass change. Okay, in general, E equals to delta mc square is used to find energy associated with any mass change. Okay, just now when I mentioned this, I told you it's used to find binding energy, right? That is correct. It's actually one of the uses of this equation. Specifically, this equation is used whenever you want to find out energy that is associated with any mass change. Because just now I told you that mass can be converted to energy, energy can be converted to mass, right? So if you want to find out whatever energy is associated with the mass change, you would actually use E equals to delta mc squared. All right, that's why here I'm using this one, because they're asking me about the mass caused by this. They're asking me about the energy caused by this mass. So you assume that your mass change is 1U. What is the energy associated with that 1U? Okay, so you use equation E is equals to delta mc square. E is equals to delta mc square. Your mass change is actually your U, 1U. Your speed of light is 2c square. Then you start subbing in your values. Okay. The value of 1U is 1.66 times 10 power minus 27 kg. The value of your speed of light is 3 times 10 power 8. You square it. Eventually, you will get your answer as 1.494 times 10 power minus 9 joules. Okay, so this one is the energy associated with a mass change of 1U. Maybe I better just write it down. It's better to like, it's easier to understand that one. This is energy associated with a mass change of 1U. That's why I can use E equals to delta mc squared. All right. So I have the answer in joules, but I want it in EV, specifically mega EV. So when I want to change to EV, I would just take the value in joules divided by 1.6 times 10 power minus 19. Okay, this is already changing it to EV. You're going to get the answer as 934 times 10 power 6 EV. I specifically left it in 10 power 6 because I want to change it to mega EV. I mean, when you go and do this, you're probably going to get the answer is 9.34 times 10 power 8 EV, right? So you want to change it to mega, it'll be 9.34 times 10 power 8 divided by 10 power 6. You're going to get mega EV, which gives you this. It's just that in my case, I actually just straight away put it in terms of 10 power 6 already, so that I can easily just convert it. Okay, you can also do the one on the right, doesn't matter. It's just a matter of your preference. Okay, so this is the energy associated with a mass change of 1 U. All right, this one so far so good. Then let me go to the next question. All right, now if you read the next question, they're asking you, find out the binding energy per nucleon in mega EV of lanthanum 139. Okay, so if you remember what binding energy was, this one is energy needed to separate a nucleus into individual nucleons to separate to infinity. Okay. To separate a nucleus into individual, what was the wording, exact wording? Separate a nucleus into individual nucleons completely to infinity. Okay, binding energy is energy needed to separate nucleus into individual nucleons completely to infinity. Okay, this is what binding energy is. What amount of energy is needed to separate one nucleus into the individual nucleons completely to infinity? So if you base on that definition, what it's actually talking about is this applied to lanthanum. All right, I'm trying to apply to lanthanum. Now, your lanthanum nucleus has 57 protons and how many neutrons? 139 minus 57 and 87 neutrons. Okay, the nucleus contains 87 neutrons and 57 protons. Now, if you want to separate them into individual nucleons, like this, neutron, you want to separate them into individual neutrons and proton, like this. Wait, let me just use the colors. If you want to separate the nucleus into the individual nucleons, like this, binding energy is the amount of energy that you have put in. Wait, let me use a different color. Binding energy is the energy that you have put in to separate this nucleus into the individual nucleons. Okay, you're going from left to right here. What is the amount of energy that you have put in order to break apart the nucleus into the individual nucleons? That one is your binding energy in the first place. So just now I mentioned to you that the masses between the nucleus and the nucleons are not the same, where I mentioned to you this one, right? Say the mass of your nucleons, mass of your nucleons when compared to your mass of your nucleus, mass of your nucleus is actually less than the mass of your nucleons, less than the total mass of your nucleons. Okay, so because mass of nucleus is less than the total mass of your nucleons, you actually have a difference in mass. You have mass defect. Okay, and just now I also mentioned to you, when you want to find out the energy associated with a mass change, you must use E is equals to delta mc squared. Okay, so if you're able to find out what is the difference in mass between the nucleus and the total mass of the nucleons, you can use this equation to find out the energy involved. So the energy involved is actually your binding energy here. Alright, so far can you follow that line of reasoning?
Yeah.
Okay, so E is equals to delta mc squared is energy, is to find energy that is associated with any kind of mass change. All right, so when you are separating your nucleus into individual nucleons, there's actually a difference in the mass when you compare the mass of the nucleus and the total mass of the nucleons. You take the mass defect, multiply with your speed of light square, you're able to find the energy. That energy so happens to be your binding energy here, because by definition, binding energy is whatever energy that you use to separate a nucleus into individual nucleons completely to infinity. Okay, so far so good with that. That's why here, if you look at the working, you try to find the mass defect first. Okay, there's a calculation here. You will see, 57 times with 1.00728 U plus with 82 times with 1.00863 U. This one is actually your use a different color. This one is actually the sum of the masses of your nucleons. 57 here is your proton. The mass of your proton is 1.00728 U. This one is from your table. And then 82 is your neutrons. Okay. So the mass of your neutron is 1.00863 U. Okay, so you adding them together is you finding the total mass of your nucleons. Okay, that is what you're doing over here. Okay, 139, oh sorry, this one is not 87, just now is 82, sorry. Okay, so this one here on the left hand side is finding mass of the nucleons. What about the other term inside your equation? 138.955 U. What is this one actually? This one is actually the mass of your nucleus. You see, it's over here, right? This is the mass of your nucleus. So I mentioned to you the mass of your nucleus and the total mass of your nucleons will never be the same. Okay, there's a difference between them. So this one here is actually the mass of your nucleus. You find the difference, you'll be able to see that it is actually 1.16762. Okay, so I mentioned early on to you just now that when you're dealing with calculations in this chapter, the mass difference is actually really, really small between the particles. So you need to work to a large number of SF. You cannot just simply work to 2 and 3 SF anymore. If they give you your data in this many SF, you use it as it is. You do not round it up. Okay, you must use it as it is, and then your final answer, you use it as it is also. Like if I do everything following the SF given in my table, this is the answer I get. You should never ever try to round it up to, let's just say 1.17 U and then proceed with your calculation. Don't do that. The only time you will ever round out your answer is when you reach your final answer. Okay, so maybe I better just write it here. Do not round up values unless it is final answer. Okay, for this particular chapter, if they give you a certain number of SF, you use it as it is. unless you reach the end, you do not ever round it out. You just use it as it is, like what I've done here. Okay, so you're going to get the mass defect as 1.16762U. Okay, so then after that, I want to find binding energy per nucleon. This one should be Be per nucleon, right? So you see, what I'm doing here is this. I took the mass defect, which is 1.16762U. I subsequently multiply with 934. This one is actually my binding energy. This one is actually my binding energy. The one at the bottom here is actually my nucleon number. In general, when you want to find binding energy per nucleon, sorry, something came out from the screen. When you want to find your binding energy per nucleon, you take binding energy divided by your nucleon number. Okay, so that's why you see here at the top, I'm finding the binding energy first before dividing by your nucleon number. So now here, my binding energy, I take the mass defect. Why do I multiply with 934 in the first place? It's because I already know how much energy is associated with 1U. You actually already found it in part 1, where you found out that if you have a mass defect of 1U, is equivalent to 934 mega EV of energy. So if your mass defect is 1.16762U, you just multiply with 934, you're going to get the corresponding energy for that mass. Okay? You're not going to be using E equals to delta mc squared here. You don't use it directly because you have already found out the energy equivalent to 1U in the first place. All right, so it's 1.1672 times 934 divided by 139. You're going to get the binding energy per nucleon as 7.85 mega EV. Okay, can? So far, so good.
Can.
All right. Okay, so this one is binding energy per nucleon. Then after that, I go to the last part. Now, the last part is asking you, state and explain whether binding energy per nucleon of uranium-235 will be greater, equal, or less than your answer in B2. Okay. So just now, you already found out this thing. Your Be per nucleon of lanthanum, your lanthanum 129 has Be per nucleon of 7.85 mega EV. Okay, this is your lanthanum. 7.85 mega EV. Okay, not 129, 139, sorry. Okay, so they're telling you right now, you already found out that lanthanum 139 has Be per nucleon of 7.85 mega EV. But now they're asking you, what if I have uranium-235? Would its Be per nucleon be greater, equal, or less than what you found in B2? So here, they're asking you to compare uranium-235. Is it greater? Sorry. Is uranium-235 going to have a Be per nucleon that is greater, less, or equal? Okay, is it greater, less, or equal? Okay, so there's actually two variations of the answer. I think it's better if I just explain based on the marking scheme answer first. That one will be the explanations in red here. You just look at the marking scheme answer first that is written in red pen here. So when you want to explain whether the uranium-235 has higher binding energy, lower binding energy, or equal binding energy per nucleon, the answer was this. when nucleon number is above 56, binding energy per nucleon decreases as nucleon number increases. Uranium-235 has a larger nucleon number than lanthanum-139. Therefore, uranium-235 has less binding energy per nucleon. This is the actual marking scheme answer. All right. Now, this one, if you just read it as it is, it probably doesn't make much sense. The reason why it doesn't make much, it will only make much sense if you try to relate it to your binding energy per nucleon versus nucleon number graph. Remember just now I told you you should memorize the graph shape. If it's binding energy per nucleon versus nucleon number, generally you have a graph shape that looks like this, where the peak always belongs to 56, ferrum 56. So you'll notice that any nucleon number above 56, the binding energy per nucleon will actually decrease. That is true. You see, if I go from 56 onwards, you will notice that your binding energy per nucleon actually will drop in value. Okay, so that one is what statement number 1 here is talking about. Anything more than 56, Be per nucleon will drop. And then after that, uranium-235 has larger nucleon than lanthanum-139. Obviously, then uranium-235 will have lesser binding energy, no? Because you try to see from the graph, lanthanum-139 will probably be here. Uranium-235 will probably be here. Because you can see that in terms of the nuclear number, uranium will be towards the right, more towards the right. So when it's more towards the right, the binding energy per nucleon is lesser. Okay, so this is for the marking scheme answer. All right. Now, the one that's written in pencil is my own answer. This one should also be more or less acceptable. Now, in your case, you notice that I wrote this here where I said lanthanum-139 is more stable than uranium-235 after nuclear reaction. The more stable a nuclei, the higher the binding energy per nucleon. Therefore, uranium-235 has less binding energy per nucleon. That one is actually referring to this equation here. You see, if you look at the first equation on the previous page, you look at the equation on the previous page, you gotta clear off everything. You look at the equation on the previous page, you started off with uranium and then you ended up with molybdenum and lanthanum. They're actually making a comparison between uranium and lanthanum. So just now I mentioned to you the goal of any nuclear reaction is to become more stable. Okay, this one is one of the first things you will learn in chemistry. Whenever a chemical reaction occurs, it is always to become more stable, not to become less stable. Okay, so you can actually kind of use the same understanding there for physics. Any nuclear reaction that occurs is always to become more stable. So if I'm talking about before reaction, which is here, this is actually less stable. But after the reaction, it's supposed to become more stable. So if I want to compare between uranium and lanthanum, then obviously lanthanum will be more stable than uranium. That's why the answer was this just now. I said that lanthanum is more stable than uranium 235 after the nuclear reaction. And generally, when some nuclei is more stable, the higher the binding energy per nucleon. Okay, so uranium-235 will have less binding energy per nucleon since it is less stable. Okay, therefore uranium-235 has less binding energy per nucleon since it is less stable. Okay, so far so good.
Yeah.
All right. Okay. So this one is okay. Then after that, I move on to some other equation calculation. Okay, next one, you can have a look at page 17. Okay, 17 maybe not. 17, 18. I think 18 would be good. Okay, have a look at page 18. Okay, this one is also teaching you how to use E equals to delta MC squared. Have a look at page 18. This is June 17, P41. Again, this one is all the way the last question. Okay, now for this particular question, they are asking you to complete the nuclear reaction again. All right. So one possible nuclear reaction that takes place in the nuclear reactor is given by this equation. Data for the nuclei and the particles are given in the table below here. These are all the particles and these are all the masses in terms of unified atomic mass. Find out for this nuclear reaction the value of X. X is this one here. They tell you you have electrons, but they never told you the number. Okay, so what you're really just supposed to do here is that you apply conservation of proton number. That is the easiest one to start with. So on the left hand side, you have 92 plus with 0. On the right hand side, it will be 42 plus with 57 plus with 0 plus with x negative 1. So x will be 7. Okay, you have 7 electrons here. Okay, so this one is okay. All right, now then show that the energy equivalent to 1U is actually 934 mega EV. Okay, so it's actually kind of like the same question like before. They're asking you to find out what is the energy associated with a mass change of 1U. Okay, so you can use E is delta MC square. Your delta M is actually 1U. In other words, just U lah. That's why it changes to UC square. The unified atomic mass is 1.66 times 10 power minus 27 kg. Multiply with speed of light square, you're going to get the answer in joules. Then you divide it into, you change it to EB. That value divide by 1.6 times 10 power minus 19 to get it in EB. And then eventually you change it to mega EB. So you're going to get that answer there. All right. Okay, so this one is okay. This is similar to what you just done. Okay, now this question, after that, they will ask you, calculate the energy in mega EV release in this reaction. Give your answer to 3 significant figures. Okay, now this one is different from what you just did. The one that you did just now was calculating binding energy. Okay, this one is also calculating energy, but it's not asking you to calculate binding energy. It's asking you to find energy released in the reaction. What we mean by that is this one. You see, your nuclear reaction is this little thing here, where we tell you is, maybe it's better if I write it now. Where we tell you is uranium-235 92 plus neutron 10 going to molybdenum 95 and 42 plus with lanthanum 139 57 plus 2 neutron 01 plus 7 11 plus with plus with 7 electron negative 10. Okay, this is the generally the reaction that's occurring. So what they want you to find is that when I went from here, the reactants to the products, which is this one, when I went from here to here, what is the energy release? Okay, bear in mind we are not talking about binding energy here. Binding energy is when we are interested in finding out how much energy did you took to break one nucleus into individual nucleons completely to infinity. Okay, that was what we did just now. This one, we have a nuclear reaction. We are interested in finding out the amount of energy that is released from the nuclear reaction. Okay, so we want to know when we went from the reactants to product, how much energy is released. Okay, so now the thing here is also this: when you go from reactants to products, what will tell you is this: the mass of your reactants, when you compare it with the mass of your products, it will not be the same. There will be a difference in the mass. Okay, when you go from reactant to product, there's actually a difference in mass also. Okay, just like when you go from a nucleus to individual nucleons, you also have a difference in mass, right? So when you're talking about nuclear reaction going from reactants to your products, you also have a mass defect. So if you want to find out the energy associated with some sort of mass defect, with some sort of mass change, I mentioned to you, you can always rely on E is equals to delta MC squared. But just now I tell you that this one is energy associated with any mass change. Yeah. Writing is getting worse and worse with this pen. Let me just write it down properly. Is energy associated with any mass change. Okay, so when you're talking about energy associated with any mass change, you always fall back on E equals to delta MC squared. It will always be used to do either two things. Okay, the first one you already did, which is to find binding energy. Okay, but when you're using finding binding energy, your delta M is actually difference in mass between product and reactant. Sorry, difference in mass between nucleus and sorry, this one is wrong. The delta M is difference in mass between nucleus and nucleons of an element. Okay, you can use it to find BE, where delta M is the difference in mass between nucleus and nucleons of an element. Like just now, you're talking about lanthanum 139. Okay, you can also use that same equation, E equals to delta MC squared, specifically to find energy release in a nuclear reaction. Okay, this is not binding energy, mind you. All right, we are talking about the energy change or energy release that came about from a nuclear reaction. Okay, you can also use E equals to delta MC squared, but here what we'll tell you is this: your delta M is the difference in mass between your product and reactant. Okay, so that's the difference here when you're talking about the delta M. If you're talking about BE, it's between nucleus and nucleons of a particular element. Okay, but when you're using E equals to delta mc squared to find energy release in a nuclear reaction like this one here, you actually use delta M as difference in mass between product and reactants. Okay, so the equations that you use is similar, just that you need to tweak a little on what is your mass defect. Okay, so that's why here you notice I'm actually taking the mass of reactant minus mass of product. I'm trying to find the difference in the mass. Okay, now you may be wondering, should I take mass of products? Can I just take mass of product minus mass of reactant? Wait, minus mass of reactant. Why is it that I take mass of reactant minus mass of product? Because mass of reactant is actually mass larger than the mass of my product. That's why I take this one minus this first. If you take mass of product minus mass of reactant, it's also fine. It doesn't matter. Okay. What we are really interested in is really just the difference. Okay. If you take mass of product minus mass of reactant, you're going to get a negative answer. That negative is fine now, actually. But what I mentioned to some people is that if you're really that concerned about getting a negative and getting it right, which one should minus which one, what I mentioned to people is that if you are really that concerned about the negative, you just put a modulus sign, okay, for both, if you wanted to. If you have difficulty memorizing which one should minus which one, you can always just put a modulus sign. Okay, if you put a modulus sign, it doesn't matter which one minus which, you will always be getting a positive value. Okay, so this is just one thing I highlight to you first now. Okay, it can be mass of reactant minus mass of product. It can be mass of product minus mass of reactant. If you want to make sure you don't get any negative, you don't want to bother about the negative, you just put a modulus sign. Okay, right? So that one should be it. Okay, so take mass of reactant minus mass of product, add up all your mass of reactant, add up all your mass of your product. Okay, mass of reactant is going to be this one. Mass of product is going to be this one. Okay, you see this one, this 235.123 and 1.00863 is uranium and neutron add together. The mass of product is all these little values that you're seeing here is actually all of these added together. Okay, so as I mentioned, don't round out your SF. Use it as it is. If they give it to you in that number of SF in your tables, use it. Don't go and round it up. So use it as it is, and then add up all the values. You will eventually get your final answer as 0.210.527U. Okay, this one is the mass defect. Now from there, you want to get the energy associated with that mass defect. Since you already found out what is the value associated with 1U, you just take that mass defect, multiply with 934, you're going to get 197 mega EV. Okay. So far, so good.
Yeah.
All right. So
For binding energy, doesn't matter if it's a reactor or product, anything can.
For binding energy, if you want to find the mass defect, same thing as before lah. If you're concerned about whether should it be mass of nucleus minus mass of nucleons, or whether should it be mass of your nucleons minus mass of your nucleus, if you're really concerned about whether you're going to get a negative, you just put a modulus sign on, you just put a modulus sign, so that you don't get negative. But by right, when I try to find binding energy, I already know that the mass of my nucleons is going to be more than my mass of my nucleus. That's why you see my working, I always take mass of my nucleons minus mass of my nucleus. But sometimes people forget which one should come first. So, and then after that, they do first, and then suddenly they find out they get a negative answer. So what I was just mentioned to people then is that if you find out you suddenly get a negative answer, just modify your existing working, just draw these two lines, modulus, then you can get rid of your negative sign. Then after that, you go and look at the part C. This is the last part. Now, the last part is asking you, suggest the forms of energy into which the energy calculated in B2 is transformed. So you already know that your energy release here is 197 mega eV. Okay, so your nuclear reaction just now gives you an amount of energy release of 197 mega eV. So what are the forms of energy that this 197 mega eV is converted to? Okay, so you could say that your energy is actually converted into kinetic energy of your products and gamma ray photon energy. Okay, now some people would somehow say that whatever energy that's released here is converted into thermal energy and light energy. It is not wrong, but there's a more specific term to it. If you've gone through ideal gas, have you gone through ideal gas?
Yeah.
Okay, you would see this equation, right? EK is actually 3/2 kT. Look familiar? Maybe no.
Yes.
Okay, so in ideal gas, you learn that kinetic energy of molecules is actually directly proportional to temperature, right? Okay, so rather than you saying thermal energy, it's more precise to say it's kinetic energy. It's your kinetic energy that that affects your temperature, which in turn affects the heat energy. So thermal energy, although it's not wrong to say that, there's a more specific term to use, which is kinetic energy of your products. It's kinetic energy that causes your heat energy in the first place. Okay. And then right now, you may see a term here called photon energy. Okay. What we'll tell you eventually is that light energy actually is photon energy. Okay. This one is actually in a different chapter called quantum physics. At this moment, you haven't learned it yet, neither in school, neither with me. But just understand this one first. When you're talking about light energy is often associated with something called photons. Okay, so although it's also correct to say light energy, it's more precise to say photon energy. Okay, your photon energy here is gamma ray photon energy. Okay, so these are the energies that this is what your 197 mega EV, your energy is converted into these two forms. Okay, they gave you 2 marks, right? 1 mark is for one form of energy. One is kinetic energy, and then one is gamma ray photon.